Okay, so we're working on this trapezoid, trying to figure out what the maximum area would be here in terms of the theta. What theta would we use to get a maximum area here? And if you remember yesterday, we wrote some expressions here for the height and the two bases in terms of r and theta. And we wound up an equation for the area here in terms of r and theta, which ultimately posed a problem because we have two variables. So the issue is there any way that we can write an equation that just relates r and theta here? And the answer for me was I couldn't find one. So bottom line though is if we simplify the expression that we wrote, we'd have that. That would be our area right there. And let's think about the fact that we have r squared here means what would be the case no matter what the r was, this value would be positive, true? And ultimately, the question is the biggest value that we could possibly get out of this area. Okay, if this is going to be positive, whatever we put in here for theta, whatever makes this the biggest would ultimately make the area the biggest then, wouldn't it? So keep in mind it's a calculator problem. So with that said, if we go to our calculator and we try the possible answers that we have here, which are the first one's 15 degrees. So if we do our sine, make sure we're in the right mode here. So sine 15, and then we do times 1 plus cosine 15. We get that. Okay. So ultimately, we're whatever we have for our r here, whatever the r value is, we're going to be multiplying it by that number. If we have, we want to try the next one, which is the 30. We change our 15s to 30s. We would get that number, which would make our total area bigger or smaller. It would be bigger. So that's that. And then we continued here with our 45. 45 would make it a little bigger yet. And then 60. 60, a little bit bigger yet. And then finally the last one, 75. 1.21 backwards, so down. So ultimately the biggest one we got would be when the angle is 60 degrees. And so therefore, choice D. Questions? Okay, what else? Anything up to 45 here on our calculator test? Okay, on 34 we got a continuous function on the closed interval -2 to 5. It says if f of -2 is 3 and f of 5 is -7, then the intermediate value theorem guarantees that what? So ultimately, intermediate value theorem, we know that f of -2 is equal to 3, and we know that f of 5 is equal to -7. So in terms of those points, if we went -2, 3, and then 5, 7, we're going from this point to this point ultimately in our graph. And so the choices that we have here is between -7 and 3 for all x, or that means that f of x is between -7 and 3 for all x between -2 and 5. So ultimately, does the theorem guarantee that, that for going from here to here, that the y values are all between the two y values in question? Or does it account for the fact that we could go up or down below those points? There's no saying whether we can go up or down below those actual y values, so that one's definitely out. The part B here says that the derivative is equal to -10/7 for at least one c between -2 and 5. That would be true if it was the mean value theorem. Okay. Mean value theorem would guarantee that the derivative would equal the slope between the endpoints at some point in the interval, but this is not what we're asking for. We're not asking for the mean value theorem, it's the intermediate value theorem. And the intermediate value theorem guarantees that part C says that there's that f of c is equal to 0, or That's D. F of C is equal to 3 for at least one C between -2 and -5. Okay. Ultimately, again, if I go between -2 and -5, we're talking about the x direction, right? If I were to go from this point to this point, somewhere in there, wouldn't I have to have crossed -3 at some point? Again, as long as this is a continuous function, this has to cross that line. Why is D no good? Yeah, it says between -7 and 3. The theorem doesn't guarantee anything between y values, does it? Okay. So ultimately, C is the only choice. E is, it says it's decreasing, and there's no guarantee it's decreasing either throughout this interval. So again, the intermediate value theorem just guarantees that going from one point to another, we have a continuous function, that every intermediate y value between, in this case, 3 and -7 is hit, okay, on our way from -2 to 5 in the x direction. What else? Anything? 45. Let's see, 44, we have 1 minus 2 cosine 2 theta as our polar curve. And the issue is, can we find the length of that polar curve? All right, we know that in general, that curve length, if we have something that's y in terms of x, that we write an integral from something to something of our the square root of 1 plus the derivative squared. If we have a polar curve, keep in mind if we were to draw the polar curve, first thing, if we were to write any kind of integral here, we need to, of course, find the upper and lower limits here. So let's see if we can graph this thing and see what we got going here. So put it in polar mode. Make sure you're in radian mode also. Got 1 minus 2 cosine 2 theta. And let's see what happens if we go from 0 to pi. See if we can get a picture here. Let me zoom in on that a little bit. Alright, so ultimately we have essentially a rose curve, if you will, that has our 4 leaves, if you will. And if you watch the sketch of it, if you will, remember, keep in mind we started at 0 for our theta values. So theta equals 0, we're at, of course, we start at -1 because we put a 0 in here, we get -1. And as we traverse that, when we got all 4 leaves drawn, it was over. True? So therefore our integral then, we used 0 and 2 pi as our upper and lower limits. Just keep in mind, once we get past 2 pi, what's it going to do again? It's just going to redraw the same thing we already had. So to get the length of that curve, okay, do that, and we do our 1 plus the derivative squared d theta. The derivative of this is going to be, of course, 0 here. Derivative of this part, derivative of cosine is negative sine. So we already have a negative, so that'd make it positive. 2 out in front would make it 4. So it'd be 4 sine of 2 theta. So let's see how that goes for us here. We got 1 plus 4 sine 2 theta. I got right parentheses here. That's good. Should be my whole integrand, I believe. 0 to 2 pi. This parenthesis. And this one. This was 40 what? 44? I got E in my notes. Correctly. Um, the one here is not correct. This is actually when polar form. I messed that up. I thought I was thinking it was 1, but it's actually r squared. Okay. So keep in mind that if it's r squared, then our r is this. So that means that the function squared is the first coordinate of that. And I'm trying to remember if I can't remember. I'll have to look again in a minute, but let's make an adjustment on that then. So we want actually. Put 1 minus 2 cosine 2 theta. You know what? Oh, you're right. 1 minus. 1 minus, and then actually I don't want that in there either. That should be good right there, huh? That needs to be squared also. Squared, that squared. Should be good unless I missed a parenthesis. See how that turns out. There we go. Alright, so that's how I got the 20.016. Alright. I want to look at the book that we use too. I want to see where that is in there. I couldn't find it at first glance, but we'll see. We might revisit that one tomorrow. Alright, so in general, keep in mind this is our polar equation. It's always going to be r squared dr d theta squared. Okay, what else? Okay. 43, we have a Hooke's law problem. And remember with Hooke's law, our force when we have a spring is always going to be a linear function kx. And it tells us that if 12 pounds of force stretches the spring 3 inches beyond its natural length, then our answer for k here would be 4. And so that means for our spring, the force equation would be 4x. So that's the first part here, is making sure that we find the force equation.
Well, when did we learn Hooke's law?
Last year. Good thing we're doing it then. So any spring is always going to be given by this force equation. Force equals k, some constant that's proportional to the length that the spring gets stretched. So bottom line here is if depending on how stretchy or not stretchy the spring is, okay, it's going to have a different constant k. And so ultimately this f equals 4x is going to be our force function. And if we want to find the work done, then the work is always going to be the integral of the force equation. So that is going to be our answer here. The limits on this, on the work done, are going to be from 0 is always going to be the natural length. And so in our case, we want to, how much work is done to stretch from the natural length, which is 0 to 6 beyond the natural length. So we go 0 to 6. And then our force equation is 4x dx. So ultimately we get 2x squared if we anti-differentiate, 6 and 0. And we get 36 times 2 would be 72. And units would be inch pounds because we're multiplying when we do this. When we do this integral of the force equation, it's inches versus pounds. Actually, I got it backwards. Pounds versus inches. So when we find the area under that curve, it would be inch pounds.